So, hello everyone. This is the first problem of today's educational round, and in this problem, we're given that a contest contains n problems with the difficulty of the ith problem is expected to be at most bi. There are already n problem proposals, and the difficulty of the ith problem is ai. Initially, both a1 to an and b1 to bn are sorted in non-decreasing order. Non-decreasing order is simply that increasing or same. Now, some of the problems may be more difficult than expected, so the writers must propose more problems. Now, when a new problem with difficulty W is posed, the most difficult problem will be deleted from the contest and the problems will be sorted in a way that the difficulties are non-decreasing. In other words, in each operation, you choose an integer W, insert it in the array sorted, non-decreasing order, and remove the last element from it. Find the minimum number of new problems to make ai less than bi for all I. So instead of like me telling you the solution, can like everybody would have been able to solve this problem. Like how did you guys solve this? If you look at the problem constraint, n is less than 100. Test cases are also less than 100, so n square would also work for this. And this is okay. So how did you guys solve? Okay, two pointer is one thing. What else? Like maybe many like everybody knows what is a two pointer. I hope. And someone used DQ. Okay. Okay. So I have also used a two pointer method. What I have done. uh, So what we can do, we can like see while our up till a point in our array A starting from beginning, there would be some values that are like more than bi, right? Once bi becomes more than a, then what? If let's say if your ai is more than b of some value, then what will you do? Like ai if ai is less than or equals to b, continue, else just increment the count and just increment j plus j. Yes, perfect. So in case you encounter that your ai is indeed more than bj or whatever like bth element at that point, you can just increment j, or you can what? You can decrement your I. Are you getting my point? Both are same. Yes, no. Like yeah. So this is a very simple problem. See, you just need to count how many places you are given an array A, A1, A2, A3, and you're given an array B, B1, B2, B3. So what you want that for every problem, A, the value A should be less than or equals to B, right? You need that for every AI is less than or equals to BA, right? Yes, no. Okay. Now, if you find that AI is more than B, just decrease your I. Why? Because now this element, because basically not increase, or like I'm saying by increasing, like this is inside a loop, right? So we are doing I plus plus in for loop. So just stay at this point and compare it with the next in J. So simply like what was told in by a student. So first, let's say I is this, J is this. If this is true for these, A1 is more than B1, So I will remain here, J will come to here. Then again do. And while you are getting these, increase your count by 1. Finally, your answer is this count. Is it clear?
Yes, sir.
Okay. So let me show you the implementation once. So this is the implementation. In this, I have this count. Instead of J, I have a K. Other than that, everything else is similar. I have two loops. I'm taking A and B as input. Then for every index from 0 to n, I'm checking if A is more than B of k plus plus. Like why k plus plus? Because I'm iterating in over my array B using this k. So if this is true, I'll increase my count by 1 and I'll decrease my I. Why I have to decrease my I? Because after this iteration, my I will again increase. So I'm trying to fix my I at this point only. And then if once I have iterated through my complete array B, that is k is more than n minus 1, that is k is now n. So I'll break my loop. So hopefully this is clear, right? Or is anyone having any doubt? Okay, perfect. So let's move to the next problem. This is the next problem, and in this problem we're given that there are n coins and there are n coins on the table forming a circle, and each coin is either facing up or down. Alice and Bob takes turn to play the following game, and Alice goes first. In each operation, the player chooses a facing down. The player chooses a facing up coin, removes the coin, and flips the two coins that are adjacent to it. So there are only two coins left. If like there are only two coins left, then one will be removed and the other won't be flipped. Why? Because it would be flipped twice. And if before the operation there is only one coin left, no coins will be flipped. And if before operation there is no facing of coins, the player loses. So we need to decide who will win the game if both players play optimally, and it can be proven that the game will end after a finite of moves. This problem, like, is just like it's like written in a verbal way that makes it a little like it seems to be a difficult problem, but the problem is very easy. So yes, this is an observation problem, kind of. So, like, can someone tell me like what is the observation in this problem, like according to you? Like, what is the one thing like this problem can be solved in two lines, like other than the input? Yes, count of you. And what specifically about count of you? Yes, perfect. Yes. So let me explain. See, there are no matter what, there are initially n coins on the table, and each of the coin is facing up or down. And another thing is they are in a circular way. So if they're in a circle, can first coin be considered adjacent to the last one? Like this is basically what circular means, right? Oh, sorry. I think my screen is blank. Just give me a second. Let me reshare it. Okay, is my screen visible now? So, like I was saying, that if we have n, like in this case 5, then we have the first and the fifth can be considered adjacent to each other. So, is that making sense or not? Like this is the case, like this is for circular, not for any other, but circular. If we have a circular arrangement, the first can be considered to last. Then we are given that in each operation, the player chooses a facing up coin and removes the coin and flips the two adjacent coins. So once these coins have been, let's say a player chooses this coin, so this is removed and these two are flipped. Now tell me one thing. If the next player chooses this, what would happen? First of all, this will be removed and then the two adjacent, that is one is flipped and the other one is not flipped, will both be flipped, right? And then we are given that if before the operation there are only two coins left, then one of them will be removed and the other won't be flipped. Why? Because it is flipped twice. Like if we had just two coins, so this is the circle. If we do operation on this, this will be removed. Like this will be removed. This will be flipped twice. So once flipped and second flipped. So no change. And if we have just one coin left, then no coin will be flipped. And if there are no coins left, then simply the player loses. So see, if we have just wait a second. Initially, like I think initially we are given a string s which determines how many coins are facing towards up, right? So tell me one thing. When this is removed, how is this changing the game? If we had two ups, how many operations can be done? If we had n coins pointing towards up, how many operations can be done? N, right? If we had, like, think about this. If we have one, we can just do one operation, that is remove it. If we have two, how many operations can be done? Two. Why? Because once you do on this and the second you do like on this, because when you do on this it will be flipped twice, so no change. Look at for three also. So when you do operation on this, both of these will be flipped, so one operation. So one operation is same as three operations. Why? Parity is same. Look out for four operations also. So if you see a pattern, in cases of odd number, you can do odd number of operations. In cases of even number, you can do even number of operations. Got it? Is this making sense? Like this is the only observation in this problem. Like you have to look for this. Yes, there is. See, for three, if I do an operation on this, yes, I'm repeating myself. See, if you just have one, if you just have one, which is up, how many operations you can do? You can do one. If you have two, you can do two operations. First operation on this will be flipped twice, and second operation on this. If you have three, you can flip this. These two will be flipped, right? They're considered like this. So for three, you can do one operation. Let's see for four also, by the way. let's say we have something like this. I remove this, I flip this. Next person can only remove this. So they flip both of these also. Now this is flipped, this is flipped. So this is now this configuration. Two operations have been done so far. And we already know that from here on, we can do two operations more. So four, total number of four operations. So for even, we have even number of operations possible. For odd, we have odd number of operations possible, and this is fixed. Is it clear? Say who wanted me to repeat? Is it clear to that person? So you just need to check how many coins are facing up. For those, your answer is like if count of u is odd, your answer is LIs. Like you can check for that case also. If you have something like up, down. So in that case also, if you remove this, one up is gone, this is flipped, this is flipped. So this becomes down, this becomes up. Effectively, one up is gone. So one up is gone. Like parity is always changing. Like if I do operation, parity changes. If you do operation, parity changes. So initially, if it is odd, Alice wins. If it is even, Bob wins. Simple as that. You can check for any configuration. Once you remove a up, a total number of ups is decreased by odd number of times. In this case, if we removed this up, the total number of ups decreased by 3 times. Is it making sense? Like you cannot change even number of times. Is it making sense? Like try for any configuration and see that if you're getting the difference even, like in the initial number of ups and in the final number of ups. Because if you got this, then it would mean that you are able to change the parity. And if you're not able to change the parity, then if you started with odd, you'll always have odd number of ups. And if you start with even, you will always have even number of ones. So if you're starting with even, you'll end up with 0. If you're starting with odd, you'll end up with lastly with 1. So that's why you then. Is it making sense? Like that's why odd and even would work. Okay, perfect. So let me show you the implementation. The implementation is really simple. This is clear to everyone, right? If you don't, like, I'm just answering like, because initially I thought this is an easy problem, so that's why I just explained it like whatever I thought was necessary. But then I looked at the questions and then I got to know, yes, these are the things that I need to explain. Like these are not that clear that once you change a up, like once you change a up, the total number of like the difference in the number of ups is always and always odd. So that's why you cannot change the parity. If you have odd, the next person will get even number of ones, you'll get odd number of ones. Again, the person, your opponent will get odd, you'll get even. He'll get odd, you'll get even. He'll get odd, you'll get even. If you start with this, you cannot change this parity. So that's why if you start with odd, at last you'll get one up and you'll win. If you start with even, eventually you'll get 0 because that is also even. So I just looked at a doubt and then like this was asked like if we have some kind of configuration, how do we prove that it will always work? Because then you cannot change the parity of number of ups. Like if you do some operation, the number of ups will decrease or increase by odd number of times. Simply that. So if it will increase or decrease by odd number of times, you'll always get the same parity of number of ups. So let me show you the implementation. Is this solution visible? So this is the implementation. We have first taken n as input, then we have taken string s as input, then we are counting how many u's are present in the string s, and if the count is odd, we print yes, otherwise no. Yes is for Li's winning, otherwise no is for Li's losing. Is it clear? Okay, so let's go to the next problem. Like I'm going very slow today because I think the first problems, the initial problems are the problems that the starters face. Like starters have difficulty understanding in. So that's why I went slow over those problems. But let's come back to this problem. Now we have that we have some cards. An integer between 1 and n is written on each card specifically for each I from 1 to n, and you have AI cards which have the number I written on them. So there is also a shop which contains unlimited cards of each type, and you have K coins you can buy. So you can buy K new cards in total, and the cards you buy can contain any integer between 1 and n. Then after buying the new card, you rearrange all the cards in a line. The score of the rearrangement is the number of contiguous subarrays of length n, which are a permutation of 1 to n. What is the maximum score you can get? So how many people were able to solve this problem? And how were you able to solve this? Like what approach did you use? Binary search to find the optimal value. See, if like how many people, like how many people for like currently in the batch for whom binary search has already been covered? Like how many students are there right now on the call for whom binary search has been covered? Like you can write yes or no. No if it isn't. Okay, if binary search has been covered, then I think it's okay if you had like a different this problem, and you have to like somehow fit and find the maximum or minimum. See, binary search is applicable on a monotonic sequence. What is a monotonic? Either increasing or decreasing. But what actually binary search, like binary search can also give you a point of maxima. Like I won't discuss this much, but you can use binary search to get a point of maxima or minima. So in this problem, we are asked to find the maximum number, like the maximum score we can get, and the score is defined as the like the rearrangement. The score of the rearrangement is the number of contiguous subarrays of length n, which are a permutation of 1 to n. So we need to form a contiguous subarrays of length n such that the subarray n has every integer from 1 to n. And we are already given that for each I from 1 to n, we have AI cards with number I written on them. So ith card, like we have ith AI cards of which have ith number written on them, and now we can use K coins, and so that we like we have K coins so that we can buy k new cards in total, and the card can have any number. So see, like if like this much is enough to know that this is a binary search problem, and that too a very simple one. See, let me explain this. So we are given some cards, like for each card we are given a number. And we are also given that k is some value. So let's say I decide that for my final score should be like, in order for my final score, I want at least two subarrays such that they are a permutation of 1 to 1. So two subarrays can be formed from this, right? Because I already have, this is one, count of one, count of two, count of three, count of four. So I already have one three times. So I can get one in both of these subarrays. I can rearrange it. Two can also be in both subarrays. So one can be in both subarrays, two can also be in both subarrays. Can three be in both subarrays? Yes, no. If that count of three is just one. No, right? So then how many times you need three more? You need three exactly one more time. Why? Because you have it once, you need it one more time. So both three can be there, four can be in both. So now how many times you used the coin, like how many extra you need just one. So one, if one is less than or equals to k, then yes, you can get two as your number of subarrays, otherwise not. So if you can get two, try for three, then try for four. So this is how we can check. But the thing is, we shouldn't check it like for each and every value. What we can do, we can check for some value here, some value here, and in between we can check. If this value is possible, then everything here is possible. Otherwise, if this value is not possible, then everything here is not possible. So this is basically binary search. I'm not going to explain this much, but this part is clear, right? On which thing binary search is being applied. Like this is monotonic. Till some point it's true. After that point, it's always false. Is it clear? Like this is a very simple problem. If you are not aware of binary search, hopefully this would make you like whatever like explanation I have given, you can solve this problem now. Is like this makes sense, right? This thing, like if you have these kinds of counts, k is some, let's say k is, you can use two times, like you can buy two cards. So yes, one is like you, in order to make two subarrays, you need one card extra, this three, because this is not present with you currently. So one is less than two, so yes, you can get two subarrays. So we are trying, yes, this is binary searching on answer. Like we are trying to get the maximum score. So for each score, we are trying to get what is the number of coins required to get that much score. And if that number of score or that number of like coins is less than or equals to k, then we can solve this. Now, what range of value should we use? Like what should be your low, what should be your high, right? This is the question that you're asking me. So what is the maximum score that you can get? And what is the minimum score that you can get? So maximum score would be like, you can take anything. What I usually do in these cases, I do this thing 10 to the power 0 and 10 to the power 18. Because why? Because this will always work. For this, like I'm not saying just blindly take, but for this problem, because if you have something like 0 to 10 to the power 6, then your solution works in log of, like your bind search work in this thing 10 to the power 6. But even if your range is this much, then your solution works in log, and this is base 2, 10 to the power 18. So this is something like, how much is this? 17, I would say 17 or 18, and this is 64. So if your solution is n into 17, it, like if this is working, n into 64 would also work. My time complexity is n log this much. Your, if you get a good range, then your probably this would be your. So in this, I have just taken this as the range. And don't take smaller range because you can get wrong answer also. In this, you can take directly as 0 and 10 to the power 18. Is it clear? Yes, no? Okay, so let me show you the code. So in this, I have taken first n and k as input. This is long. Remember, you need to take long because the values are given such in the input. Then I'm taking array a count of each value number in input. I'm applying binary search. Low is this, high is this. I'm finding mid. Answer is nothing but like how many eventually how many elements I have and how many sub-arrays. Like these are the elements. If I want mid as my answer, then I should have how many elements. If I want mid as the number of those, mid as my score. So like this is just for taking, see, this is like mid is my score, so I would have at least mid plus n minus 1 elements. Why? If I have mid plus n elements, then technically I would have how many subarrays? Mid plus 1 subarrays. If I have mid plus n elements, I can have mid plus 1 subarrays, right? Yes, no? If I want just mid subarrays, mid number of subarrays, how many maximum number of elements you can have? Mid plus n minus 1. Okay, let me explain this also. Did you get it or do you want me to explain? If you have if you want 3 subarrays and your n is 5 and you need 3 subarrays, what is the maximum number of elements? What is the maximum number of elements? 3 into 5 plus 5 minus 1. Is it making sense? N minus 1. Why 12? How did you come up with 12? Okay, yes, no problem. So if you later on divide this by n, you will get how many subarrays you have, right? So we just need to do like iterate over your elements and check if their count is more than like if you can divide this into like for each count of AI, just see if this count AI can be divided into, let's say, whatever the total number of elements divided by n. So this is this thing score, and I have written it here like this is pretty misguiding. This value is not the score. This value is the number of elements. This is your score. This is your score, right? So if this is true, then I have this temporary variable, which is t, which I have initialized here. So I increase it that, okay, this is okay. Otherwise, if this is not okay, I have simply calculated how much extra do I need. So this is the extra do I need. This is the number, this is the score, like I said, this is the score, and this is what I already have. So this is what I need. So need is added. Then if there are some elements left, like those are also added in this. Like I said, answer is not the actual score, but answer is the number of elements. So if you divide it by n, you'll be left with something. So you need to make like if answer modulo n is something is left, so you need to cover those also, right? So you out of t, like we are adding those also, whatever is left. And finally, if need is less than k, this is simple binary search. If need is like whatever you need is less than or equals to k, that is you can possibly have it. So low is shifted to mid, you can have at least ls your answer. Otherwise, high is shifted to mid minus 1. Finally, we can print the low. So like instead of like directly looking like, instead of considering this as a solution, like binary search can be applied in many ways. This is one of the ways. And this computation is specific to mine. If you implement your binary search, probably you'll get some other computation. Like this math part is, this is dependent on the solver who is writing the solution. But the idea of binary search remains this, what I have explained here. Is it clear? What do you mean by need where I? Okay, need is basically if you decide that you are going to have score as something, then how many coins you need in order to get that score. So need is basically, let's say, like I have explained here, my screen is visible, right? This thing. You need X as your score. This X, you have some counts of each and every card. So if you need X as your score, let's say each card should be at least this many times. So this card and let's say this card is not up to this mark. So you need to keep using K points. So you keep adding this in new, and finally you can check that the number of points that you need is whether less than or equal to K or not. Is it making sense? Okay, perfect. Perfect. So to the next problem. Now the next problem is, okay, sorry, my screen. Yes, now my voice breaking for everyone. Now it's ready. But I'm not in a connection, so it's not. It's not breaking. Yes. Okay, am I audible right now? Okay, let me know in case you guys feel that my voice is breaking or something. So in this problem, we're given that we have two positive integers n and m, and we need to calculate the number of ordered pairs which satisfy the following condition. A is between 1 and n, b is between 1 and m. A plus b is a multiple of b times GCD of a and b. So if you look at the problem constraint, there can be 10 to the power 4 test cases, and it is guaranteed that neither the sum of n nor the sum of m exceeds 2 into 10 to the power 6 for over all the test cases. So let me write the equation first. We need to find the number of ordered pairs A and B, how many these exist, such that A is between 1 and n, B is between 1 and m, A plus B is a multiple of B times is a multiple of B times GCD of A and B. So how many people were able to solve this problem? This is also, I would say, a observation only. So A plus B modulo B times GCD of AB is 0. Okay. Okay, how were you able to solve this? Like, what approach did you use?
Yeah, I actually used a mathematical formula. Like I reduced this equation.
Which equation?
This equation, like that you have written, it's that a plus b should be divisible by b dot gcd
Yes.
a comma b. So I took it like I just wrote it in some form like y is your gcd of a comma b. So this yes gcd,
Yes.
and then a plus b will be divisible by b dot y.
Yes.
So then like b is a constant factor, which ultimately means that a plus b should be also like in some form of a multiple of b.
Yes. This is also right. A should be a multiple of B, like B times X, something like B times Y is also correct.
Exactly, like b dot x. And since b is already there, so which means that a is also a multiple of like b only.
A is a multiple of B, because
Yes,
if A is not a multiple of B, then how can, like, A plus B is written in form of B times X. So A is can be B times something like alpha, right? Then
yes. And then one interesting thing is that gcd of like some multiple of b and b will be b only.
B alpha plus B
Yes,
and
yes,
have B times X. And we already know that A plus B modulo B times GCD. And now GCD of, if I write this in this form, which is B alpha plus B. The only common term here is B. So greatest common divisor of these two will be B. So A plus B divided by B square, right?
yes,
Like A plus B should be divisible by B square, right?
yes,
Yes. So if I break this further down, I have A divided by B plus 1 divided by B. Can I write this thing as this?
yes,
A
correct.
by B plus 1 should be divisible by B. Is this thing making sense to everyone? Otherwise, I'll repeat. So you just need to, if you go from 1 to m and you have a fixed n, like for n, first find, you just need to find, if you go from, like, let me explain this quickly again. So up till here, it's clear that R A plus B should be divided by B square. Now, from here, we can go in any way. But what I have done, I have gone from 1 to m. Let's say I'm iterating using I. I just need to count for this how many possible values if I is currently my B is currently I. So how many values of A are possible in N such that, like, they are between 1 and N. So first of all, see that how many values of X are there such that I have N divided by I plus 1, this thing. And eventually this should be divisible by this I. So how many values are divisible by I? Exactly X by I values are divisible. If you have 5 for in 5 1 to 5, how many values are divisible by 3? 5 by 3. How many values are between 1 and 7 are divisible by 3? 7 by 3. And this is low, like, floor. So for every I from 1 to m, iterate and find x like this, find y like this, add to your answer y. Is it clear? This is possible when we are able to iterate. In the hard version, we won't be able to iterate. So that's why the same solution cannot be submitted for that problem. For this, the solution is this much. Just go through the values from 1 to m, count how many possible values of x there are, and for those, just find how many of in among up till x, 1 to x, how many values are divisible by I. So that is x by I. Add that to your answer. Finally, we can print our answer. But there is one thing, I'm decreasing my answer by 1. Why? Can anyone tell me why?
It's like there was for one there will be one extra count. Like I also did the same thing.
Yes, for 1 there is an extra count for 1 1. Right? You're counting the pair 1 1. Right. So that needs to be removed. And other than that, this is the solution. For 1 y we are for 1 y, like if you plug in 1 in this equation, you'll see that n by 1 plus 1. So you get n plus 1, and you'll get for y you'll get n plus 1 options, but n plus 1 options are not true. From 1 to n there are n unique values. So how you are getting n plus 1? So that's why answer minus minus. So that's it. And if you have any doubts regarding this, you can raise a query. Like I feel like many people wouldn't, like if you haven't solved binary search earlier, or if the binary search hasn't been covered yet, you might need some more guidance. So you can raise a query and I'll explain how binary search actually works. So that's it. Thanks for joining, and bye bye.